Section 2.4, we're going to look more about slope and lines and the equations of lines. The first thing to look at is to talk about slope and parallel lines. It says here if two non-vertical lines are parallel, then they have the same slope. And conversely, if two distinct non-vertical lines have the same slope, then they're parallel. In other words, parallel lines never intersect, and as far as their slope goes, it'll be the same slope. Also, we understand that two parallel lines with undefined slope are vertical lines. So two distinct vertical lines, both with undefined slope, are parallel. Perpendicular is when the two lines make a 90-degree angle with each other, and so two non-vertical lines are perpendicular if the product of their slopes is -1. Another way to compare the slope of perpendicular lines is that the slopes are negative reciprocals of each other. Conversely, if the product of slopes of two lines is -1, then that means that they're perpendicular lines. Also, this says the understanding we have that a horizontal line with zero slope is perpendicular to a vertical line having an undefined slope. And so what we're going to do is look at a few examples where we talk about the equations of lines with parallel and perpendicular slopes. The first one says if the slope of a line is two different slopes, we have m equals -1/2 and m equals 2, what would be the slope of the line parallel and perpendicular to these slopes? Well, starting with a -1/2, the slope parallel to that would be the same slope, so it would also be -1/2. Perpendicular, however, what we do is we take the negative reciprocal of the slope. So what that means is reciprocal means we flip it around, so it would become 2/1, and we take the negative of the number. The number was already a -1/2, so we do a negative of a negative of the reciprocal, which just turns it into a positive 2/1, or just positive 2. For a slope of 2, parallel would be the same slope, so it would also be 2. Perpendicular, on the other hand, we take the reciprocal of 2, which is 1/2, and we do the negative reciprocal, so that would be -1/2 is the negative reciprocal of 2, and that would be the slope perpendicular to it. On this one, we're going to deal with the equations of lines. In this one, we want an equation of the line passing through -3, 1, and parallel to the line with the equation y equals 2x plus 1. And we'll write it in slope-intercept form. So if it's parallel, the parallel slope would be the same slope as we have in this equation. Since this equation is in the form of y equals mx plus b, slope-intercept form, 2 is the slope. M is equal to 2. So parallel slope would also be 2. We're going to use the -3, 1 as our point, x1, y1 over here. And we're going to use point slope form to create the equation. So y minus y1 equals mx minus x1. So it'll go y minus 1 equals 2x minus -3. Or in other words, y minus 1 equals 2 times x plus 3. We're going to go ahead and solve for y, since we want to write this in slope-intercept form when we're done. So I'm going to distribute the 2, make it into y minus 1 equals 2x plus 6. And from there, I'll add the 1 over. And this will be equation of the line y equals 2x plus 7. This one says, write the equation of the line passing through the point 3, negative 5 and perpendicular to the line whose equation is x plus 4y minus 8 equals 0. So this one needs to be solved for slope-intercept form. So we want to write it in y equals mx plus b form so that we can figure out what the slope is. Because once we know what the slope of that line is, then we can know what the slope for perpendicular is. So in order to solve this equation, first thing I'm going to do is I'm going to go ahead and add this 8 over. So x plus 4y equals 8. We're going to go ahead and subtract the x over. So we'll get 4y equals negative x plus 8. And then I'm going to divide through by 4. So that'll turn this into y equals, technically this negative x could be thought as negative 1x. So let's think of that as negative 1 over 4x plus 2. So now we can look at this equation and recognize that the slope is negative 1 over 4. And then we can think about what is it perpendicular to that. Perpendicular slope here would be the negative reciprocal. So negative, negative, we'll flip it around to 4 over 1. So that would be just positive 4 for a slope perpendicular. The point that it says to use here is the 3, negative 5 point. So that'll be our x1 and our y1 to use with point slope form. So y minus y1 equals mx minus x1. So y minus negative 5 equals 4. We're using our perpendicular slope times x minus 3. So we'll distribute the 4 here. This is going to turn into y plus 5 equals 4x minus 12. We can subtract the 5 over from both sides and have y equals 4x minus 17. This one says write the equation of the line in slope-intercept form passing through the point negative 1, 5 and perpendicular to the line whose equation is x equals 6. One thing to recognize is this is an equation that is already a vertical line. So if we think about what's going on here, let's locate that point negative 1, 5. So we have this vertical line passing through x equals 6, like so. And so perpendicular to a vertical line would be the horizontal line. The equation of a horizontal line is y equals b. So if we want to draw a line passing through this point perpendicular to the other line, it would be a horizontal line. It passes through the number 5. And so the equation for the horizontal line would be y equals 5. The next thing we're going to talk about in regards to slope is how we can interpret slope as a rate of change. In this one it says find a linear equation which models the given description. In 1950, Americans spent 22% of their budget on food. This has decreased at an average rate of approximately 0.25% per year since then. One way we can visualize this is by plotting some of the values we have. For instance, in the first year it says it was 22% spent on food. And then every year after 1950 it declines by 0.25%. So 1 year after 1950, it would decline to 21.75%. 2 years, it would decline to 21.50%, and so forth. Every year declining by the same amount. So it follows what we refer to as a linear trend, because every year it decreases by the same amount, at least up to a certain point, but that trend holds for several years. We can create an equation of the line by using our linear functions, linear equations. Here, since it's declining by that much per year, that essentially amounts to the slope. It's the rate at which it changes per year, declining in this case. So m would be equal to negative 0.25. Negative because it's declining. So we know that about the slope. The point at which it starts will be the y-intercept. So the y-intercept is called b in slope-intercept form, so that would be 22. So if we use the equation of a line for y equals mx plus b, this can be modeled with negative 0.25x plus 22. Now the last example had to deal with a strictly linear situation with a linear equation. However, not every function or every situation can be represented or modeled by a linear equation. In such cases, we'll have an average rate of change rather than the same rate of change everywhere on the function. So this is the formula for average rate of change. It goes f of x2 minus f of x1 divided by x2 minus x1. This is for a function f between the values of x1 to x2. The average rate of change essentially is the same thing as the slope of a line, which we call the secant line through 2 points in the graph, x1 comma f of x1 and x2 comma f of x2. So in the picture you can see how the curve goes up and down and does a lot more things than a straight line does, but we can draw a straight line through 2 points, determine the slope of that line. Since that line goes through 2 points, that's what we call the secant line of the curve between those 2 points. We find the slope of that line by using this formula, and that's also the same as the average rate of change between those 2 points. So let's do something with average rate of change. This is going to be for the function f of x equals 4x squared minus square root of x between the values of x1 equal to 1 and x2 equal to 4. So we calculate this using average rate of change formula, doing f of 4 minus f of 1 divided by 4 minus 1. What I'll do is go ahead and calculate f of 4 and f of 1 on their own. To do f of 4, we'll do 4 times 4 squared minus the square root of 4. That comes out to be 64 minus 2, or 62. F of 1 would be 4 times 1 squared minus the square root of 1. That would be 4 minus 1, or 3. So in our average rate of change formula up on top, we'd have 62 minus 3 divided by 4 minus 1. That would equal to 59 over 3. And we could leave it as a fraction or leave it as or calculate it to a decimal, depending on what we want to do. For now, I'm just going to leave it as 59 over 3. Now here's some actual data we can use to think about average rate of change. Obviously this picture we see here isn't along a straight line. It curves up and then down. So when we try to find rate of change, we'll be doing it by an average between 2 points. It says this is actually graph of average high temperatures in Greenville. And so what we're going to do is find the average change in monthly average temperatures between March and June and September to November. So first off, from March to June time frame would be between the 3rd month for March and the 6th month for June. For March, we have a data point of 3,72, and for June, we have a data point of 6,92. Essentially what we're going to do is find the average rate of change between those months. But again, we treat it as a slope, in this case of the secant line between those 2 points, where we can calculate the slope using these as x1, y1 and x2, y2 for average rate of change. So that would look like here 92 minus 72 divided by 6 minus 3. That comes out to be 20 divided by 3. Now I will go ahead and divide and round off this number to, let's say, 6.67 degrees. That's the degrees per month on average that the temperature is changing between those months. Now the next part up above says for September to November. So let's look at the graph and get those numbers. Okay, September would be the 9,89, and the November would be the 11,70. So we'll figure out the average rate of change here again. For September to November, this will be our x1, y1, x2, y2. And if we calculate using those numbers, we're going to get 70 minus 89 divided by 11 minus 9, which comes out to be negative 19 over 2. And when I divided those, I came out with negative 9.5 degrees per month, which makes sense since the temperature is declining between those 2 months. What we can do with data points often is create a function to fit as best as possible through the points with a curve. And so the graph of this function here, f of x equals all the stuff, is an approximation for the temperatures. We're going to use it to determine the averages between average rate of change between March to June and September to November. So we're going to start off by doing the March to June average rate of change. We're going to be using the average rate of change formula. March is the 3rd month, so we're going to be using 3, and June the 6th. So we'll be using x1 equal to 3 and x2 equal to 6. In the average rate of change formula, it would go f of 6 minus f of 3 divided by 6 minus 3. Now the awkward part here is calculating f of 6 and f of 3. I'll go ahead and plug them in so you can see what they would look like inside the function when we have to calculate them. So if I do f of 6, this is what it's going to look like. I'm just using the function from up above, and I'm substituting in the number 6 for x. When I did the calculation for that, and I had to round it off to 93.5, we'll do something similar for f of 3. Having substituted 3 in here and running the numbers, came out with 69.12. So these are the numbers I have to use to calculate the average rate of change. On top would be 93.5 minus 69.12 divided by 6 minus 3. When I did the calculation there, I came out with approximately 8.13, and that just stands for degrees per month. For September to November, we're going to be using September, that'll be our x1 equal for 9, and x2 for November, that'd be for 11. So we're going to calculate f of 11 minus f of 9 divided by 11 minus 9. Now I calculated f of 11 and f of 9 much like the last one, so I had to plug it in and run the numbers. For f of 11, I got 69.12. For f of 9, I came out with 87.96. So that's divided by 11 minus 9. So when I ran the numbers on that, it came out to be rounded off to negative 9.42 degrees per month. So to compare the difference between the actual values from the data points and the values received from our function in the average rate of change formula, the actual was 6.67 when we did the March to June, and the function came out with 8.13. So that one would be off by 1.46 degrees per month. In the case of the other one, which was September to November, the actual was negative 9.5, and our function, we came out with negative 9.42. So that one's not off by quite as much. That one's only off by 0.08 degrees per month.